Hello there, and welcome back to the Sleepless Astronaut channel. I'm truly glad you've chosen to spend this evening with me. There's something special about the nighttime, isn't there? The world quiets down, the rush of the day fades away, and we're left with space to think, to wonder, to let our minds wander to places they don't usually go during the busy daylight hours. Tonight, we're going to one of those places together. Somewhere strange. Somewhere that challenges everything we think we know about reality itself. Tonight, we're going to fall into a black hole. Now, before you tense up at the thought, let me assure you that this is the safest possible way to experience such a journey. You're lying comfortably wherever you are right now. Maybe you're in bed, surrounded by soft pillows and warm blankets. Maybe you're in a chair, feet up, ready to let the day slip away. Wherever you are, you're safe. You're grounded here on Earth, protected by our atmosphere, warmed by our sun, held gently by gravity that's just strong enough to keep you comfortable, but not so strong that you feel crushed. What we're about to do is take a journey of imagination. We're going to use science as our guide, physics as our map, and we're going to explore what would happen if a human being could somehow approach and fall into one of the universe's most mysterious objects. Along the way, we'll learn about the nature of space and time, about gravity and light, about stars and their deaths, and about the fundamental strangeness of the cosmos we inhabit. So settle in now, take a slow, deep breath. Feel the air filling your lungs, then releasing. Notice how your body feels against whatever surface is supporting you. Notice the weight of your limbs, the softness of fabric against your skin, the temperature of the air around you. You're here, you're present. You're safe. And for the next while, you're going to let me guide you through one of the most fascinating thought experiments in all of science. Let your eyes close if they haven't already. Let your breathing find its natural rhythm. Slow, steady, easy. There's nowhere you need to be. Nothing you need to do. Tonight, you're an explorer of ideas, a traveler through cosmic possibilities. And our destination is a place where the rules of reality bend so severely that everything we take for granted simply stops making sense. We're going to a black hole. The very name sounds ominous, doesn't it? Black hole. Like something from a nightmare or a science fiction horror story. A hole in space that's utterly, completely black. But black holes are real. They exist throughout the universe. And while they are indeed strange and extreme, and in some ways terrifying, they're also natural consequences of physics, no more supernatural than a sunset or a raindrop. They're what happens when gravity wins absolutely and completely, when matter collapses so far that it punches through the fabric of space itself. But I'm getting ahead of myself. Before we can understand black holes, before we can imagine falling into one, we need to understand where they come from. And that means we need to talk about stars. Because black holes are born from the deaths of stars, at least the smaller ones are. The massive ones at the centers of galaxies have more complicated origins, but we'll get to those later. For now, let's talk about stars. Close your eyes and picture the night sky. Imagine you're somewhere far from city lights, somewhere the sky is truly dark. You look up and see thousands of points of light scattered across the darkness. Stars, each one a sun, many of them far larger and brighter than our own sun. Some of them are relatively close, cosmically speaking, just a few light years away. Others are hundreds or thousands of light years distant, and every single one of them is a massive ball of hydrogen gas, held together by its own gravity, generating energy through nuclear fusion in its core. Our sun is a star, a perfectly ordinary, middle-of-the-road star. It's been shining steadily for about 4.5 billion years, and it will continue shining for another 4.5 billion years or so before it runs into trouble. The sun is neither particularly large nor particularly small. It's not especially hot or especially cool. It's right in the middle of the range, what astronomers call a G-type main sequence star. Yellow, medium-sized, stable. The kind of star that gives its planets plenty of time for interesting things to develop. Things like oceans and atmospheres and, eventually, life. The sun works through a process called nuclear fusion. At its core, where the temperature reaches about 15 million degrees and the pressure is enormous beyond imagining, hydrogen atoms are slammed together with such force that they overcome their natural electrical repulsion and fuse, combining to form helium. This process releases energy, a lot of energy. The sun converts about 4 million tons of matter into pure energy every single second through Einstein's famous equation, E equals mc squared. That energy works its way up through the layers of the sun over thousands of years, eventually reaching the surface and radiating out into space as light and heat. The light that warms your face on a sunny day started as fusion reactions deep in the sun's core thousands of years ago. It's been bouncing around inside the sun ever since, gradually working its way outward until finally it escaped from the surface, crossed the 93 million miles of empty space between the sun and Earth in about 8 minutes, passed through our atmosphere, and reached you. You're being warmed by ancient starlight, by energy that's been traveling for millennia to reach you. The sun is in a state of balance. Gravity is constantly trying to crush it inward, to compress it down to the smallest possible size. But the fusion reactions in the core create tremendous heat and pressure that push outward, resisting gravity's squeeze. These two forces, inward gravity and outward pressure, balance each other perfectly. The sun is in equilibrium. It's stable, and it will remain stable for billions of years to come. But not all stars are like the sun. Some stars are much, much larger, 10 times more massive, 20 times, 50 times, 100 times more massive than our sun. These giant stars burn brilliantly, shining with the light of thousands or millions of suns. They're spectacular, beautiful, the brightest objects in any galaxy. But they pay a terrible price for their brilliance. They live fast and die young. You see, a star's lifetime depends on its mass, but not in the way you might expect. You might think a more massive star, having more fuel, would live longer. But the opposite is true. A more massive star has more fuel, yes, but it burns through that fuel at a far faster rate. The core of a massive star is hotter and denser than the core of a smaller star, so fusion happens much more quickly. A star 10 times more massive than the sun might live only 20 million years instead of 10 billion. A star 50 times more massive might live only a few million years. They're cosmic mayflies, brilliant but brief. And when these massive stars run out of fuel, when they've fused all the hydrogen in their cores into helium, they don't just fade away gently like smaller stars do. They keep going. They start fusing helium into carbon and oxygen, and carbon into neon and magnesium, then neon, then oxygen, then silicon, each stage requiring higher temperatures and lasting for shorter periods of time. The star becomes like an onion. with layers of different elements burning at different depths. Hydrogen burning in a shell around the core, then helium, then carbon, and so on, all the way down to silicon burning in the very center, creating iron. And then everything stops. Iron is special. It's the most stable element in the universe. If you fuse lighter elements into iron, you release energy. But if you try to fuse iron into heavier elements, you don't get energy out. You have to put energy in. Iron is a dead end. There's no energy to be gained by fusing it further. So when the core of a massive star turns to iron, fusion stops. The core is no longer generating the heat and pressure needed to hold the star up against gravity. The outward pressure vanishes, and gravity wins. What happens next takes less than a second, but it's one of the most violent events in the universe. The core collapses. Not slowly, not gradually, but catastrophically. The iron nuclei are crushed together. The electrons, which normally orbit the nuclei and atoms, are squeezed into the protons, combining with them to form neutrons. The entire core of the star, which might have been thousands of miles across, suddenly compresses down to something only about 10 or 15 miles in diameter. A ball of pure neutrons, a neutron star. The collapse happens so fast that it creates a shock wave. The outer layers of the star, still falling inward, suddenly encounter this incredibly dense neutron core and bounce. The rebound creates an explosion of unimaginable violence. The star tears itself apart. For a few weeks it shines with the light of billions of suns. We call this a supernova, and it's one of the most energetic events in the universe. During the supernova, something remarkable happens. The extreme temperatures and pressures create conditions where fusion can continue beyond iron. Elements heavier than iron are created in those brief moments of explosive violence. Gold, platinum, uranium, all the heavy elements in the periodic table are forged in supernova explosions and scattered into space. The gold in any jewelry you might own, the uranium in nuclear reactors, the platinum in catalytic converters, all of it was created in the death throes of massive stars billions of years ago, then scattered across space, eventually incorporating into the cloud of gas and dust that formed our solar system. You're surrounded by the ashes of dead stars. You're made of them. But we were talking about neutron stars, weren't we? These remnants of stellar cores compressed down to incredible densities. Let's take a moment to appreciate just how strange neutron stars are, because they're remarkable objects in their own right, and understanding them will help us understand black holes. A neutron star is small, roughly the size of a city, 10 or 15 miles across, but it contains more mass than the sun. All that mass, compressed into such a small volume, creates a density that's almost incomprehensible. A teaspoon of neutron star material would weigh about 1 billion tons. If you could somehow scoop up a teaspoon of neutron star and bring it back to Earth, it would weigh as much as a large mountain. It would punch through the Earth and probably come out the other side, creating a hole straight through the planet. The gravity on the surface of a neutron star is about 100 billion times stronger than Earth's gravity. If you could stand on a neutron star, which you absolutely couldn't, you would weigh as much as a large mountain. The gravity would crush you instantly, flattening you down to a layer only a few atoms thick. You'd become part of the surface, spread out in a thin film. Neutron stars also spin very fast. When a star collapses, it conserves angular momentum, which means the rotation rate increases dramatically. It's like when a figure skater pulls their arms in during a spin and suddenly rotates much faster. A star that was rotating once every month or so before collapse might end up rotating hundreds of times per second after becoming a neutron star. Some neutron stars have powerful magnetic fields and emit beams of radiation from their magnetic poles. As the star spins, these beams sweep across space like a lighthouse beam sweeps across the ocean. If one of these beams happens to point toward Earth, we detect a pulse of radiation every time the star completes a rotation. We call these objects pulsars, and they're remarkably precise cosmic clocks. Some of them are so regular that they rival atomic clocks in their time-keeping accuracy. When pulsars were first discovered in the late 1960s, their regularity was so startling that astronomers briefly considered the possibility that they might be artificial, perhaps signals from an advanced alien civilization trying to communicate across the galaxy. They even jokingly labeled the first pulsar LGM-1, standing for Little Green Men. But it turned out to be a natural phenomenon, just an extraordinarily precise one. The universe is full of natural clocks, rhythms, and cycles that tick away with mathematical precision. Take a slow breath now. Feel your chest rising and falling. Notice how your body is settling deeper into relaxation. We're building up a foundation of understanding, layer by layer, so that when we finally approach our black hole, you'll have the context to appreciate what's happening. There's no rush. We have all the time in the world, or rather all the time outside of worldly concerns. Time is becoming soft and flexible for you now, isn't it? The minutes are blurring together into a gentle flow. Neutron stars are extreme, but they're not the most extreme objects in the universe. Because if the collapsing core of a dying star is massive enough, if there's enough matter falling inward, the collapse doesn't stop at the neutron star stage. It continues. The neutrons themselves can't withstand the pressure. They're crushed together, compressed beyond what even the strong nuclear force can resist. The core continues to shrink, smaller and smaller, denser and denser, and at some point something remarkable happens. The escape velocity from the surface exceeds the speed of light. Escape velocity is the speed you need to break free from a gravitational field. On Earth, the escape velocity is about 7 miles per second. If you throw a ball up at less than 7 miles per second, it will eventually fall back down. If you could throw it faster than 7 miles per second, it would escape Earth's gravity and fly off into space. The escape velocity from the Sun's surface is much higher, about 380 miles per second. From a neutron star, it's about half the speed of light. But if the collapsing core is massive enough, if the compression continues far enough, eventually the escape velocity reaches and then exceeds the speed of light. And that's when you have a black hole. Nothing in the universe can travel faster than light. This is one of the bedrock principles of physics, discovered by Einstein in his theory of special relativity and confirmed by every experiment and observation since. The speed of light isn't just very fast. It's the maximum possible speed woven into the fundamental structure of space and time. Light always travels at light speed. Nothing with mass can reach light speed, and nothing, absolutely nothing, can exceed it. So if the escape velocity from an object exceeds the speed of light, then by definition, nothing can escape from it. Not rockets, not particles, not radiation, not even light itself. And if light can't escape, the object appears black, it's invisible. A hole in space. This is a black hole. Not a hole in the sense of an absence, but a region of space where gravity has become so strong that it traps everything, including light. The boundary around a black hole, the point of no return, is called the event horizon. It's not a physical surface. There's nothing there you could touch. It's simply a mathematical boundary in space, marking the distance from the center at which the escape velocity equals the speed of light. Cross the event horizon going inward, and you can never come back. Every possible path you could take, every trajectory you could follow, leads deeper into the black hole. Outward is no longer a direction you can travel. The geometry of space itself has been so warped by gravity that all routes lead inward, toward the center, toward the singularity. Black holes come in different sizes, and for our journey tonight, we need to choose our destination carefully. The smallest black holes, called stellar mass black holes, or sometimes just stellar black holes, form from the collapse of massive stars, just like we've been discussing. These might be anywhere from a few times the mass of the Sun to perhaps 20 or 30 solar masses. The event horizon of a stellar mass black hole might be only a few miles across, small but unimaginably dense. All that mass compressed into a region the size of a small city. There are probably millions of these stellar black holes scattered throughout the Milky Way galaxy, invisible remnants of massive stars that died long ago. We can sometimes detect them if they're part of a binary system orbiting a normal star. Gas from the normal star gets pulled toward the black hole, forming a swirling disk that heats up and emits X-rays before crossing the event horizon. We can see those X-rays and infer the presence of the black hole, even though we can't see the black hole itself. Then there are intermediate mass black holes, ranging from perhaps 100 to 100,000 solar masses. We're not entirely sure how these form. They might be stellar black holes that have been feeding, growing larger over time as they consume gas and stars. Or they might form through other processes, perhaps from the direct collapse of huge clouds of gas in the early universe, or from the merging of many stellar black holes in dense star clusters. We've detected hints of these intermediate black holes, but they're relatively rare and mysterious. They occupy a strange middle ground between stellar and supermassive black holes, and understanding how they fit into the cosmic picture is an active area of research. And then there are the giants, the supermassive black holes. At the center of nearly every large galaxy in the universe, there sits a supermassive black hole, not just big, monumentally, incomprehensibly massive. The black hole at the center of our own Milky Way galaxy, an object called Sagittarius A*, and pronounced Sagittarius A star, weighs about 4 million times as much as the Sun. That's 4 million solar masses of matter, all compressed into a region smaller than Mercury's orbit around the Sun. The event horizon would be about the size of the Sun itself, even though it contains 4 million times more mass. And that's actually on the small side for supermassive black holes. Some galaxies have black holes at their centers that weigh billions of solar masses. The largest black hole we know of, sitting at the heart of a distant galaxy, weighs about 66 billion times as much as the Sun. Imagine that. 66 billion stars worth of mass, all concentrated in a region of space that, while large by human standards, is tiny compared to the galaxy it sits in. How did these monsters form? That's a question astronomers are still working to answer completely. They might have grown gradually over billions of years, starting as stellar mass black holes in the early universe and feeding on gas and stars, merging with other black holes when galaxies collided, slowly accumulating mass like cosmic snowballs rolling downhill. Or they might have formed early in the universe's history through different mechanisms, perhaps from the direct collapse of enormous clouds of primordial gas, creating massive black holes right from the start. The truth is probably some combination of these processes, varying from galaxy to galaxy. What we do know is that supermassive black holes are common. Almost every large galaxy has one at its center. They sit at the galactic cores, often surrounded by dense clusters of stars packed much more tightly than anywhere else in the galaxy, and they shape the evolution of their host galaxies through their immense gravitational influence. Some astronomers think that the growth of the central black hole and the growth of the galaxy are intimately connected, two aspects of the same cosmic story playing out over billions of years. And this brings us to an important decision for our thought experiment tonight. Which kind of black hole should we fall into? We need to choose carefully because the experience would be very different depending on the size of the black hole. If we chose a stellar mass black hole, we'd have a problem. A serious, uncomfortable problem called tidal forces. Let me explain what these are and why they matter so much. Tidal forces are differences in gravitational pull across an object. Imagine you're falling feet first toward a black hole. Your feet are closer to the black hole than your head, right? So they experience slightly stronger gravity than your head does. This difference stretches you. It pulls your feet down harder than it pulls your head, elongating your body. On Earth, tidal forces are gentle and barely noticeable in everyday life. The moon's gravity creates tides in the ocean by pulling on the water facing it slightly more strongly than it pulls on the Earth's center, and pulling on the Earth's center slightly more strongly than it pulls on the water on the far side. This creates bulges in the ocean, which we experience as high and low tides. The effect raises the water level by a few feet twice a day. You don't feel stretched when you stand on the beach because the tidal forces on your body are incredibly tiny. Near a black hole, especially a small one, tidal forces are not gentle at all. They're extreme, violent. The gradient of gravity is incredibly steep. If you were falling toward a stellar mass black hole, by the time you got anywhere near the event horizon, your feet might be experiencing gravity thousands or even millions of times stronger than your head, even though your head and feet are only 6 feet apart. This difference would stretch you like taffy, pulling you longer and thinner. We call this process spaghettification, and yes, that really is the scientific term for it. As you approached a stellar mass black hole, long before you reach the event horizon, the tidal forces would become unbearable. You'd be stretched vertically, elongated like a piece of pasta, while simultaneously being compressed horizontally as gravity pulled everything toward the black hole's center. Your body would become thinner and longer. Eventually, the forces would exceed what molecular bonds can withstand, and you'd be torn apart. Your body would cease to exist as a coherent structure and would become a stream of particles, all falling toward the black hole in a thin line like spaghetti. This doesn't sound particularly pleasant for a bedtime story, does it? It would make for an uncomfortable journey into sleep. So we're not going to a stellar mass black hole. We're making a smarter choice. Instead, we're going to a supermassive black hole. And here's why this makes all the difference in the world, or at least in our thought experiment. With a supermassive black hole, the event horizon is much, much farther from the center. Remember, the more massive the black hole, the larger the event horizon. And because the event horizon is so far from the center, the curvature of space there is actually quite gentle. The tidal forces near the event horizon of a supermassive black hole are surprisingly mild. Think about it this way. When you're at the event horizon of a stellar mass black hole, you're only a few miles from the singularity at the center, so the gravitational gradient is incredibly steep. But when you're at the event horizon of a supermassive black hole, you might be millions of miles from the center. The gravitational gradient is much more gradual. Your head and your feet, 6 feet apart, are experiencing almost the same gravitational pull because they're both almost exactly the same distance from the center, relatively speaking. This means you could actually cross the event horizon of a supermassive black hole without feeling anything particularly unusual, at least not right away. No violent stretching, no immediate spaghettification. You just cross this invisible boundary in space, and from your perspective, everything would seem normal. At least at first. The spaghettification would still happen eventually, but only later, deeper inside the black hole, much closer to the center, where the tidal forces finally become extreme. But you'd have time before that happened. Time to experience what it's like inside an event horizon. Time to observe the strange effects of being in this region of space where the rules are different. So for our peaceful journey towards sleep, for our comfortable exploration of cosmic mysteries, we're choosing a supermassive black hole. We want to experience the strangeness without the immediate violence. We want to cross the event horizon and see what's on the other side. Let's say we're approaching Sagittarius A*, the 4 million solar mass supermassive black hole that sits at the center of our Milky Way galaxy. It's about 26,000 light years away from Earth, which means the light we see from that region of the galaxy left there 26,000 years ago, long before recorded human history, long before the invention of agriculture or writing or cities. That light has been traveling through space all this time, and it's just now reaching our telescopes, giving us a window into the distant past. But for our purposes tonight, we've already made the journey somehow. Perhaps we have a ship that can travel faster than light, which physics says is impossible. But this is imagination, so we'll bend the rules just this once. We're here now, approaching the galactic center, and ahead of us we see something remarkable. We don't see the black hole itself, of course. It's black, it's invisible. Light can't escape from it, so there's nothing to see. But we can see its effects on everything around it. There are thousands of stars orbiting nearby, packed much more densely than anywhere else in the galaxy. The galactic center is a crowded place, with stars separated by distances much smaller than the distances between stars out here in the galactic suburbs where Earth lives. All these stars are held in their orbits by the black hole's tremendous gravity, and some of them are moving incredibly fast. There's a star called S2 that orbits Sagittarius once every 16 years. That might not sound particularly fast until you realize how big the orbit is. This star is moving at speeds up to 5,000 miles per second, about 2% of the speed of light. By carefully tracking S2's orbit over many years, astronomers have been able to confirm that it really is orbiting a supermassive black hole, and to measure that black hole's mass precisely. We might also see an accretion disk though Sagittarius doesn't have a particularly bright one right now. An accretion disk is a swirling spiral of gas and dust that's falling toward the black hole, like water spiraling down a drain. As this material falls inward, particles rub against each other, friction heats them up, and the disk begins to glow. It emits radiation across the spectrum, from radio waves to visible light to X-rays. Some accretion disks around black holes are incredibly bright. The brightest ones around the most actively feeding supermassive black holes can shine with the light of trillions of suns. We call these objects quasars, and they can be seen from billions of light years away. For decades, astronomers didn't understand what quasars were. They just looked like extremely bright points of light, brighter than anything else we'd ever seen. It wasn't until the 1980s that we figured out they were supermassive black holes at the centers of very distant galaxies, surrounded by brilliantly glowing accretion disks as they devoured enormous amounts of matter. For our journey, let's imagine there's a disk around Sagittarius A*, glowing softly, marking the location of the invisible monster at its center. A beautiful, eerie spiral of light against the darkness, showing us where we need to go. And now, we're going to begin our descent. We're going to fall in. Take another slow, deep breath. Feel how relaxed you are now. Your body is heavy, sinking comfortably into whatever surface supports you. Your mind is quiet, drifting peacefully through these ideas. We're about to cross into one of the strangest regions of space, but you're completely safe. This is imagination. This is a thought experiment. And there's something deeply peaceful about contemplating the cosmos, isn't there? About letting your mind expand to think about things so much larger than everyday concerns. As we begin our descent toward the black hole, moving inward from a safe distance, the first thing we notice is that something strange is happening to time. This is one of the most profound and counterintuitive discoveries of Einstein's general relativity. Time is not absolute. It doesn't flow at the same rate everywhere in the universe. Instead, time is affected by gravity. The stronger the gravitational field you're in, the slower time passes for you relative to someone in a weaker gravitational field. This effect is real and measurable. GPS satellites orbiting Earth several thousand miles up experience slightly weaker gravity than we do on the surface. As a result, time runs slightly faster for them than it does for us. The difference is tiny, just microseconds per day, but it's real. If we didn't account for this effect, GPS coordinates would drift by several miles per day, making the whole system useless. Atomic clocks placed at different altitudes tick at measurably different rates. Time truly does run at different speeds in different gravitational fields. Near a black hole, this effect becomes dramatic. The gravitational field is so intense that time dilates significantly. As we fall toward the event horizon of Sagittarius, imagine that someone is watching us from far away, from a safe distance where gravity is weak, perhaps from a spaceship orbiting a distant star. What would they see? They would see us moving slower and slower as we approach the event horizon. Our spacecraft would appear to be decelerating, our movements going into slow motion. If we waved to them, the wave would look like it was happening underwater, sluggish and drawn out. The light from our spacecraft would change too. It would shift toward the red end of the spectrum, becoming redder and dimmer. This is called gravitational redshift. As photons climb out of the intense gravitational field near the black hole to reach the distant observer, They lose energy, and losing energy means their wavelength gets longer, shifting toward the red. The closer we got to the event horizon, the more extreme these effects would become. We'd appear to move slower and slower, approaching the horizon asymptotically, seeming to take forever to actually reach it. Our image would grow dimmer and redder. Eventually, we'd appear to freeze right at the event horizon, our spacecraft hovering there motionless, fading gradually from view, but never quite crossing that invisible boundary. To the distant observer, we would never fall into the black hole. They'd watch us get closer and closer to the event horizon, slowing down more and more, until we appeared to stop completely at the horizon and simply fade away. From their perspective, we'd be stuck there forever, frozen at the moment of crossing. This is what general relativity predicts, and it's deeply strange. But here's the even stranger part. That's not what we experience. From our perspective inside the spacecraft, time feels completely normal. Our clocks tick at the same rate they always have. We don't feel ourselves slowing down. When we look at the clock on the dashboard, the seconds tick by normally. When we look at each other, we move and speak normally. Nothing feels different. And we don't freeze at the event horizon. We don't even slow down. From our point of view, we just keep falling inward, accelerating as we go, and we cross the event horizon without any sensation of passing through anything at all. The event horizon from the inside is not a place. It's not a barrier or a wall. It's just an invisible line in space. There's no sign that says you are now crossing the event horizon. There's no feeling, no sound, no change in what we see or feel. We just cross it, as naturally as crossing any other imaginary line, like the equator or the Arctic Circle. But we have crossed a boundary. We've crossed the ultimate point of no return. And even though we don't feel any different, everything has changed. We're inside now, inside the event horizon, inside a black hole, and we're approaching the place where this first part of our journey will pause, because there's so much more to explore, so many more wonders and mysteries waiting for us. But for now, rest here with this image. We've crossed the event horizon. We're inside. And ahead of us, deeper in the black hole, stranger things await. Your breathing is slow and peaceful. Your body is completely relaxed. Part of this story is complete, and soon we'll continue the journey together. But for this moment, just rest. Just breathe. Just be. So here we are, inside the event horizon of a supermassive black hole. We've crossed the boundary that separates the universe outside from this strange realm inside. And even though we crossed it without feeling anything dramatic, even though our clocks are ticking normally and we feel fine, something profound has changed about the nature of space and time around us. Let me try to explain what's happened, because this is one of the most mind-bending aspects of black holes, and it's worth taking our time to understand it. Your mind is relaxed now, open to strange ideas, floating peacefully through these cosmic thoughts. So let's drift together through this weirdness. Outside the event horizon, in the normal universe where you're lying right now in your comfortable bed, space and time work the way you're used to. You can move freely through space. You can go left or right, forward or backward, up or down. Space is your domain. You have freedom there. But time is different. You can't control time. You can't stop it, can't reverse it, can't do anything except move forward through it at a steady rate. Time flows from past to future, always inevitably, carrying you along whether you want to go or not. Inside the event horizon, something remarkable happens. The extreme warping of space-time causes the rules of space and time to trade places in a certain mathematical sense. The inward direction, toward the singularity at the center of the black hole, stops being a direction in space that you can choose to move in or not. Instead, it becomes like time. It becomes inevitable. Just as you can't avoid moving forward in time outside the black hole, you can't avoid moving inward once you're inside the event horizon. It's not that something is pulling you inward, though gravity is certainly strong. It's that the geometry of space-time itself has been bent so extremely that all possible paths through space-time, all possible futures, lead inward toward the center. Imagine you're driving a car and you realize the road only goes one direction. You can turn the steering wheel all you want, but no matter which way you turn it, the car keeps going in the same direction. That's a bit like what's happening here, except it's not a road that's forcing you. It's the fundamental structure of space and time itself. You could fire your rockets at full power, pointing away from the center, trying desperately to escape back to the outside universe, but you'd still move inward toward the singularity. The rockets would work fine. They'd push you just as hard as they always did. But outward is no longer a direction that exists for you to travel. All directions, every possible direction you could point, leads deeper into the black hole. This is hard to visualize because we're not used to thinking about space behaving like time does. We're used to space being something we can navigate freely and time being something that drags us along. But inside an event horizon, space-time is warped so severely that these intuitive distinctions break down. The mathematics describes it clearly, even if our intuitions struggle. Inside the horizon, reaching the singularity at the center is as inevitable as reaching tomorrow was outside the horizon. You can delay it slightly by firing your rockets, just as you can delay tomorrow slightly by traveling very fast, which makes time pass slower for you. But you can't avoid it. The singularity is in your future, unavoidably the way tomorrow is always in your future. Take a slow breath. Let this strangeness wash over you. You don't need to fully grasp it. Just appreciate the weirdness of it. The universe is far stranger than our everyday experience suggests. Reality is more flexible, more bizarre, more wonderful than we could have imagined. As we continue falling deeper into the black hole, we're still feeling relatively normal. Remember, we chose a supermassive black hole specifically because the tidal forces near the event horizon are gentle. We're inside now, yes, but we're still far from the center, and so far we're okay. But as we fall deeper, as we get closer to the singularity at the heart of the black hole, we start to notice something. A pulling sensation, a stretching. The tidal forces are beginning to make themselves felt. Your feet, being closer to the center than your head, are experiencing slightly stronger gravity. It's subtle at first, just a gentle pulling, like someone's lightly tugging on your feet. But as we fall deeper, the effect grows stronger and stronger. The gravitational gradient becomes steeper. The difference between the pull on your feet and the pull on your head increases. You start to feel stretched, elongated, like you're being gently pulled apart. At the same time, you feel pressure from the sides, because all the gravity is pulling everything toward the same point at the center. So you're being compressed laterally while being stretched longitudinally. This is spaghettification beginning. At first, it's just uncomfortable. Then it becomes painful. Your body is being deformed by forces it wasn't designed to withstand. You're getting longer and thinner, stretched like taffy being pulled. The forces continue to increase as we fall deeper. What was painful becomes unbearable. What was unbearable becomes destructive. Eventually, the tidal forces exceed what the molecular bonds in your body can withstand. Your cells begin to come apart. Your tissues separate. You're being pulled apart at the molecular level. First, your body breaks into large pieces. Then those pieces break into smaller pieces. And then the pieces break down into individual cells, then molecules, then atoms. You're becoming a stream of particles, all following the same path inward toward the singularity, but no longer organized into anything resembling a human being. No longer organized into anything at all. This sounds horrifying, and in reality, it would be. But remember where you actually are right now. You're safe in bed, warm and comfortable, breathing slowly and peacefully. This is just imagination, just a thought experiment. We're exploring what would happen, not experiencing it. And there's something almost poetic about the idea, isn't there? Your atoms would be joining the black hole, becoming part of it, adding your mass, tiny as it is, to the tremendous mass already there. In a sense, you'd become one with the black hole, your particles falling into the singularity at the center, becoming part of that mysterious point where all the mass resides. The singularity. Let's talk about what that is, or what we think it is, because this is where our understanding of physics truly reaches its limit. According to Einstein's general relativity, all the mass of a black hole is concentrated at a single point at the center. Not a small point, an infinitely small point. A point with no size whatsoever, no volume, no dimensions. Just pure mass compressed into a mathematical abstraction called a singularity. At this singularity, the density becomes infinite. The curvature of space-time becomes infinite. The tidal forces become infinite. Everything becomes infinite, and that's a problem. Infinity is a red flag in physics. When your equations produce infinities as answers, it usually doesn't mean that something is actually infinite in reality. It means your equations are breaking down, being pushed beyond their valid range, into a regime where they no longer accurately describe what's happening. Think of it like trying to use a map of your city to navigate on the moon. The map works great for its intended purpose, but it's the wrong tool for a completely different environment. General relativity is like that map. It works beautifully for describing gravity in most situations, even extreme ones like near neutron stars. But at the very center of a black hole, conditions are so extreme that general relativity starts giving nonsensical answers. Most physicists believe the singularity isn't actually a point of infinite density. Instead, they think it's a region, probably very small, but not infinitely small, where quantum effects become important, where we need a quantum theory of gravity to describe what's really happening. The problem is we don't have such a theory yet. Not a complete one, anyway. We have general relativity, which describes gravity beautifully on large scales, but doesn't include quantum mechanics. And we have quantum mechanics, which describes particles and fields beautifully on small scales, but doesn't include gravity in a fundamental way. What we need is a theory that combines both, that describes how gravity works when quantum effects are important. We need quantum gravity. There are candidates for such a theory. String theory is probably the most famous one. It proposes that fundamental particles aren't really point-like objects, but tiny, vibrating strings of energy. These strings are incredibly small, far smaller than atoms or even subatomic particles. And in string theory, space has more than the 3 dimensions we're familiar with. It has 9 spatial dimensions, maybe 10, with the extra dimensions curled up so small we can't perceive them. String theory is mathematically beautiful and makes some interesting predictions, but it's extremely difficult to test. The energies required to probe the scales where string theory becomes important are far beyond what our particle accelerators can achieve. So for now, it remains a fascinating idea that might be right, but we can't confirm it. Loop quantum gravity is another approach. It suggests that space itself isn't continuous, but is made of discrete units at the smallest scales, like pixels on a screen. Space is quantized, broken up into tiny chunks that can't be subdivided further. In this view, the singularity might be a very small but finite region where space-time is maximally compressed, squeezed down to these fundamental quantum units, but not compressed beyond them. Both theories suggest that when you fall to the center of a black hole, you don't encounter a point of infinite density. Instead, you reach a region, tiny but not infinitely tiny, where quantum effects dominate and the rules of classical physics no longer apply. What happens in that region? What would you experience? We honestly don't know. The mathematics becomes too difficult, the physics too speculative. It's possible that the singularity is a place where space and time themselves break down, where those concepts stop making sense. It's possible that quantum fluctuations become so violent that reality itself becomes probabilistic and uncertain in a way we can't currently describe. It's possible that there are connections to other regions of space-time, maybe even to other universes, though that's highly speculative. The truth is, we don't know, and that's okay. That's even beautiful, in a way. After all the progress science has made, after all the mysteries we've solved, there are still places where our knowledge runs out, where we reach the boundary of what we can explain. The center of a black hole is one of those places, but you'd never be able to tell anyone what you found there, even if you somehow survived to experience it, because nothing escapes from inside a black hole. The event horizon is a one-way membrane. Information can fall in, but nothing comes back out. Or so we thought until Stephen Hawking came along. In the 1970s, Hawking made a remarkable discovery that changed how physicists think about black holes. He found that black holes aren't entirely black after all. They emit radiation, a very faint, very slow trickle of particles leaking out from near the event horizon. This radiation is now called Hawking radiation, and it's one of the most profound results in theoretical physics. Hawking radiation happens because of quantum effects near the event horizon. You see, in quantum mechanics, what we think of as empty space, vacuum, isn't really empty. It's filled with quantum fluctuations, with pairs of virtual particles that pop into existence, exist for a brief moment, and then annihilate each other. These virtual particles appear in pairs, a particle and its antiparticle, an electron and a positron, for example. They're called virtual because they don't normally last long enough to be observed directly. They borrow energy from the vacuum to exist, but they have to pay it back almost immediately by annihilating each other. It's like taking out a loan that you have to repay instantly. Near the event horizon of a black hole, something interesting can happen. A virtual particle pair can appear right at the edge of the horizon. One particle might fall into the black hole while the other escapes into space. The escaping particle is now real, not virtual, because it's separated from its partner and can't annihilate. It carries away energy as it escapes. But energy can't be created from nothing. So where does the energy for this real particle come from? It comes from the black hole's mass. The black hole loses a tiny amount of mass every time a particle escapes. Very slowly, particle by particle, the black hole evaporates. For a large black hole like Sagittarius A*, this process is unimaginably slow. The rate of Hawking radiation depends on the black hole's mass. The more massive the black hole, the lower its temperature and the slower it radiates. A supermassive black hole like Sagittarius has a temperature just above absolute zero, far colder than the background radiation left over from the Big Bang. It's actually absorbing more energy from the universe than it's radiating away, so it's growing, not shrinking. But in principle, if the universe expands and cools enough, if we wait long enough, eventually even supermassive black holes will begin to evaporate. The process would take an incomprehensibly long time, far longer than the current age of the universe. But given enough time, trillions upon trillions of years, a supermassive black hole would slowly radiate away its mass and eventually disappear. Smaller black holes evaporate faster. A stellar-mass black hole would take longer than the current age of the universe to evaporate, but not as long as a supermassive one. And a very small black hole, if one existed, would evaporate quickly. As a black hole loses mass, it gets hotter and radiates faster. The process accelerates. Near the end, a small black hole would evaporate explosively, releasing all its remaining energy in a final burst. This raises a fascinating puzzle that physicists are still arguing about. It's called the black hole information paradox. In quantum mechanics, information is never truly destroyed. If you know the quantum state of a system at one time, you can in principle calculate what the state was at any earlier time or will be at any later time. Information is conserved. The universe doesn't forget. But what happens to information that falls into a black hole? If the black hole later evaporates completely through Hawking radiation, where does that information go? According to Hawking's original calculation, the radiation coming out is completely random, determined only by the black hole's mass, charge, and spin. It doesn't carry any information about what fell in. If you threw an encyclopedia into a black hole and then waited for the black hole to evaporate, the Hawking radiation wouldn't tell you anything about the encyclopedia. The information would be lost. But that violates quantum mechanics, which says information can't be destroyed. So either quantum mechanics is wrong, which seems unlikely given how well tested it is, or something else is going on. Some physicists think the information isn't lost, but is encoded in subtle correlations in the Hawking radiation. Maybe the particles coming out aren't truly random, but are correlated with each other in ways that preserve the information about what fell in. The correlations would be incredibly difficult to detect, requiring you to collect and analyze vast amounts of the radiation, but in principle, the information might be there. Others think the information is stored somehow on the event horizon itself, encoded in microscopic quantum structures at the boundary. When the black hole evaporates, this information is released with the final burst of radiation. Still, others think we need to modify our understanding of either general relativity or quantum mechanics, or both, to resolve the paradox. Maybe the singularity isn't really singular. Maybe there are connections inside black holes to other regions of space-time where the information goes. The question remains open, debated at conferences, worked on by brilliant theorists. And there's something wonderful about that. Here's a fundamental question about how the universe works, and we don't know the answer yet. We're still figuring it out. Science is still actively discovering new things about reality. Rest with that thought for a moment. Breathe slowly. Feel how relaxed you are, how peaceful. We've traveled deep into a black hole, explored its mysteries, and now we're going to step back and think about the bigger picture, about the universe and our place in it. Let's leave the black hole now in our imagination. Let's pull back, return to the safety of empty space, and think about all the other wonders the cosmos contains. Because black holes, as fascinating as they are just one type of strange object among many. There are magnetars, for example. These are a special type of neutron star with magnetic fields so intense they defy comprehension. The magnetic field of a magnetar is about 1,000 trillion times stronger than Earth's magnetic field. If you could somehow bring a magnetar to the distance of the moon from Earth, its magnetic field would be strong enough to erase every credit card on the planet. If you got within a few hundred miles of a magnetar, the magnetic field would be strong enough to disrupt the molecular bonds in your body. You'd simply come apart at the atomic level, not from tidal forces, but from the sheer strength of the magnetic field warping the electron orbits in your atoms. Magnetars occasionally have what we call starquakes. The crust of the neutron star, stressed by the intense magnetic field, suddenly cracks and rearranges itself. When this happens, the magnetic field reconfigures explosively, releasing more energy in 1/10 of a second than the sun releases in 100,000 years. These bursts of energy are so intense that they can be detected from thousands of light years away, and they can briefly affect Earth's ionosphere when they reach us. There are gamma-ray bursts, which are even more energetic. These are the brightest electromagnetic events in the universe, brief explosions that can outshine entire galaxies for a few seconds. They happen when massive stars collapse into black holes or when neutron stars collide and merge. The explosion creates two jets of material and radiation shooting out at nearly the speed of light. If one of those jets is pointed at Earth, we see a gamma-ray burst. If a gamma-ray burst happened in our galaxy and was pointed at us, it could be catastrophic. The burst of radiation could strip away our ozone layer, exposing the surface to harmful ultraviolet light from the sun. This could trigger mass extinctions. Some scientists think that certain mass extinctions in Earth's past might have been caused or contributed to by distant gamma-ray bursts. Fortunately, gamma-ray bursts are rare, and the odds of one happening close enough and pointing at us are extremely low. We're probably safe, probably. There are hypervelocity stars moving so fast they're escaping the galaxy entirely. These stars were likely flung out by gravitational encounters with the supermassive black hole at the galactic center. They approached the black hole in binary pairs, got too close, and one star was captured while the other was flung away at tremendous speed. Some of these hypervelocity stars are moving at over 1,000,000 miles per hour, fast enough to escape the Milky Way's gravity and travel out into intergalactic space. Imagine being on a planet orbiting one of these stars. You'd be leaving your home galaxy, embarking on a journey into the vast emptiness between galaxies, never to return. In a few 100 million years, you'd be floating in the cosmic void, with the Milky Way, a distant spiral of light behind you, and the nearest other galaxy millions of light years away. You'd be truly alone in the universe, isolated on your island of light in an ocean of darkness. There are rogue planets, worlds that don't orbit any star at all. They drift through interstellar space, alone in the dark. Some were ejected from their original solar systems by gravitational interactions with other planets or passing stars. Others might have formed independently, condensing from clouds of gas and dust without ever being part of a solar system. These rogue planets are cold. Without a star to warm them, they're probably frozen solid, with surface temperatures just a few degrees above absolute zero. But some might have thick atmospheres that trap heat from radioactive decay in their cores. Some might have subsurface oceans kept liquid by tidal heating if they have large moons. It's possible, though unlikely, that some rogue planets could harbor life in these hidden oceans, surviving without sunlight. We don't know how many rogue planets are out there. They're very hard to detect because they don't emit light, and they're not near stars that could illuminate them. But based on simulations and the few detections we have made, there might be billions of them in our galaxy alone. More rogue planets than stars, perhaps, all wandering invisibly through the darkness between the stars. Space is full of wonders. Some beautiful, some terrifying, all fascinating. And then there are the mysteries, the things we know exist but barely understand. Dark matter is perhaps the biggest mystery in cosmology. We know it's there because we can see its gravitational effects. Galaxies rotate too fast for the gravity of their visible matter to hold them together. They should fly apart, but they don't. Something invisible is providing extra gravity, keeping them intact. Galaxy clusters also move in ways that require more mass than we can see. When we measure the total mass of a galaxy cluster by observing how galaxies move within it, we get a much larger number than when we add up all the visible matter. There's something there we can't see, contributing most of the mass. The large-scale structure of the universe also requires dark matter. The way galaxies are distributed in space, forming filaments and walls surrounding vast voids, can only be explained if there's much more matter than we can see, providing the gravitational scaffolding on which visible matter accumulated. When we add up all the evidence, we find that about 85% of the matter in the universe is dark matter. Everything we can see, all the stars and galaxies and gas clouds, all the normal matter made of protons and neutrons and electrons, accounts for only about 15%. We're the minority. We're made of the rare stuff. What is dark matter? We don't know. The best guess is that it's a new type of particle that doesn't interact with electromagnetic radiation. It doesn't absorb light, doesn't emit light, doesn't reflect light. It only interacts through gravity and possibly through the weak nuclear force. Physicists have built incredibly sensitive detectors trying to catch dark matter particles. These detectors are placed deep underground, shielded from cosmic rays and other interference, waiting for a dark matter particle to collide with a normal atom. So far, after decades of searching, we haven't definitively detected anything. Dark matter remains elusive and visible, a cosmic ghost haunting the universe. Some scientists think dark matter might be primordial black holes, tiny black holes formed in the early universe rather than from collapsed stars. Others think it might be something even stranger, like modifications to gravity that make it behave differently on large scales. But most physicists favor the particle hypothesis. We just haven't found the right particle yet. And then there's dark energy, which is even more mysterious than dark matter. In the late 1990s, astronomers were studying distant supernovae, using them as cosmic distance markers to map the expansion of the universe. Everyone expected to find that the expansion was slowing down over time, decelerated by the gravitational pull of all the matter in the universe. The question was just how much it was slowing. But that's not what they found. They found that the expansion wasn't slowing down. It was speeding up. The universe is expanding faster now than it was billions of years ago. Gravity should be pulling everything back together, but instead, something is pushing space apart, causing the expansion to accelerate. We call this something dark energy, but that's really just a name for our ignorance. We don't know what it is. The best current explanation is that it's a property of space itself, a kind of energy inherent in the vacuum. As space expands, more space is created, and with it comes more dark energy. This creates a feedback loop. More space means more dark energy, which causes faster expansion, which creates more space, which creates more dark energy, and so on. Dark energy makes up about 68% of the total energy content of the universe. Dark matter is about 27%. Normal matter, the stuff we're made of, is only about 5%. 95% of the universe is dark, invisible, made of things we don't understand. That's humbling, isn't it? We've learned so much about the cosmos, mapped the universe to incredible distances, understood the life cycles of stars and the evolution of galaxies. But we still don't know what most of the universe is made of. We're like map makers who've charted the coastlines but haven't explored the interior. We know the outlines, but the details remain mysterious, and that's beautiful. That means there's still so much to discover, still so many questions to answer, still mysteries waiting to be solved by future generations of scientists. The universe is about 13.8 billion years old. It began in the Big Bang, or perhaps emerged from some prior state we don't yet understand. It's been expanding ever since, cooling and evolving. In the first moments, it was a hot, dense soup of energy and particles. As it expanded and cooled, particles combined to form atoms. Then gravity pulled those atoms together into clouds. Then those clouds collapsed to form the first stars. Then stars clustered into galaxies. Then galaxies clustered into groups and clusters and superclusters, forming the cosmic web we see today. The observable universe, the part we can see, is about 93 billion light years across. That's larger than you might expect for a universe that's only 13.8 billion years old, because space itself has been expanding. Light from distant galaxies has been traveling toward us for billions of years, but during that time, space has been stretching, carrying those galaxies even farther away. But the observable universe is just the part we can see. The universe beyond our cosmic horizon might be much larger. It might even be infinite. We don't know. We may never know. Light from regions too far away will never reach us, no matter how long we wait, because the expansion of space carries them away faster than light can cross the expanding space. We live in one galaxy among hundreds of billions in the observable universe. Our galaxy, the Milky Way, contains hundreds of billions of stars, and most of those stars probably have planets. The more we've looked, the more planets we've found. It seems that planets are the norm, not the exception. Almost every star has at least one planet, and many have multiple planets. Some of those planets are in the habitable zone, the region around a star where temperatures are right for liquid water to exist on the surface. And where there's liquid water, there might be life. Life as we know it requires water. It needs a solvent for chemistry to happen, a medium for molecules to interact. Water is perfect for this, and it's common throughout the universe. Are we alone in the universe? It seems unlikely. The universe is so vast, so full of stars and planets, that the emergence of life seems almost inevitable somewhere. Maybe life is common. Maybe every habitable planet develops simple life. Maybe some fraction of those develop complex life. Maybe some fraction of those develop intelligent life. Maybe some fraction of those developed technological civilizations. But we haven't found anyone yet. We've been listening for radio signals from alien civilizations for decades. We've been looking for signs of artificial structures or industrial activity on distant planets. We've found nothing. The universe is silent as far as we can tell. This silence is puzzling. It's called the Fermi paradox, named after physicist Enrico Fermi, who famously asked, "Where is everybody?" If intelligent life is common, we should have detected some sign of it by now. The fact that we haven't is strange and requires explanation. Maybe intelligent life is rare. Maybe the jump from simple single-celled organisms to complex multicellular life is difficult. Maybe the evolution of intelligence is unlikely. Maybe technological civilizations are common but short-lived, destroying themselves through war or environmental catastrophe before they can spread to the stars. Maybe the distances are just too vast. Even if there are thousands of civilizations in our galaxy, they might be separated by thousands of light years. Communication would take thousands of years. Travel would take even longer. Maybe we're all isolated on our little islands of rock and water, unable to bridge the vast oceans of space between us. Or maybe we're just not looking in the right way. Maybe aliens don't use radio waves to communicate. Maybe they use technologies we haven't invented yet or can't imagine. Maybe they're here observing us, but we don't recognize them. Maybe they exist in forms so different from us that we wouldn't recognize them as life. We don't know, but we keep looking, keep listening, keep hoping that one day we'll detect a signal, find a sign, make contact with someone else out there in the cosmic dark. And even if we never find anyone, even if we're truly alone, that's profound too. It would mean we're the only part of the universe that woke up, that became conscious, that started asking why. We'd be the universe's way of knowing itself, the only witness to cosmic beauty, the only beings capable of appreciating how wonderful existence is. You're part of that story. You're made of atoms forged in ancient stars. The iron in your blood was created in a supernova explosion billions of years ago. The calcium in your bones, the carbon in your cells, the oxygen you breathe, all of it came from stars. You are literally made of stardust. And not just physically. Your consciousness, your thoughts, your sense of self, these all arise from the laws of physics, from chemistry and biology, and neuroscience, from the same principles that govern stars and galaxies. You're not separate from the universe, you're a part of it, an integral, meaningful part. Through your eyes, the universe sees itself. Through your thoughts, the universe contemplates its own existence. You're a pattern of matter and energy that's become aware, that can look up at the night sky and feel wonder, that can ask questions about origins and meanings and purposes. That's extraordinary. That's beautiful. Even if you're tiny compared to the cosmos, even if your life is brief on cosmic timescales, you matter. You're here. You're conscious. You're aware, and that's a gift, a privilege, a remarkable thing to be. Right now, as you lie here listening to this, you're on a planet orbiting a star. That star is orbiting the center of a galaxy. That galaxy is moving through space relative to other galaxies. You're traveling through the cosmos at tremendous speeds, but you don't feel it. You feel still, at rest, because everything around you is moving with you. The Earth is spinning on its axis at about 1,000 miles per hour at the equator. It's orbiting the Sun at about 67,000 miles per hour. The Sun is orbiting the center of the Milky Way at about 500,000 miles per hour, and the Milky Way itself is moving through space at over 1,000,000 miles per hour relative to the cosmic microwave background radiation. You're on a cosmic journey hurtling through space at incredible speeds, but you feel peaceful, still, calm, because motion is relative, and from your perspective, you're at rest. Tomorrow the sun will rise, not because the sun is moving, but because the Earth is rotating, turning your location toward the sun's light. Life will continue. Birds will sing. People will go about their days. The universe will keep doing what it's been doing for billions of years, spinning and expanding and evolving, and you'll be part of it. Living your life, making your choices, experiencing your moments of joy and sorrow and wonder, adding your small but meaningful chapter to the vast story of existence. But for now, for tonight, just rest. Let go of everything. The day is done. Tomorrow can wait. Right now, in this moment, there's nothing you need to do except breathe and drift and let sleep come. You've journeyed far tonight. You've fallen into a black hole, or at least imagined it. You've crossed the event horizon, experienced the warping of space-time, contemplated singularities and Hawking radiation, and the mysteries at the boundary of knowledge. You've thought about neutron stars and magnetars and gamma-ray bursts. You've considered dark matter and dark energy, the invisible components that make up most of the universe. You've pondered whether we're alone in the cosmos or whether other minds are out there, wondering the same questions. It's been a long journey through ideas and wonders, and now it's time to let those ideas fade, to let your mind quiet, to let sleep embrace you gently. Close your eyes if they're not already closed. Feel your breathing, slow and deep and rhythmic. Feel your body, heavy and relaxed, sinking into the bed. Feel how peaceful you are, how calm, how ready for sleep. The black hole is far away, 26,000 light years away, at the heart of the galaxy. The mysteries can wait. The questions will still be there tomorrow. But tonight you've done enough. You've explored enough. You've wondered enough. Now just be, just rest. Just let yourself drift into that soft, dark space between waking and sleeping, that peaceful realm where thoughts dissolve and consciousness fades and dreams begin. You are stardust. Ancient atoms organized into a temporary pattern called you. You're connected to everything that exists, everything that has existed, everything that will exist. You're part of the grand cosmic story that began 13.8 billion years ago and continues to this moment. You belong here. You're exactly where you should be. Safe on your planet, under your atmosphere, warmed by your star, held gently by gravity that's been working perfectly for billions of years. Sleep well, cosmic traveler. Dream of stars and galaxies if you dream at all. Dream of black holes and event horizons, of the vast ocean of space in which we float, or dream of nothing. Let your mind go quiet and dark and peaceful. The universe holds you. It always has. It always will. You're home. You've always been home. And the cosmos that made you, that gave you atoms and energy and consciousness, watches over you as you sleep. Rest now. Drift. Let go. Tomorrow is far away. Tonight you're safe. Breathe slowly. Feel your heartbeat, steady and calm. Feel yourself sinking deeper, floating gently into sleep. Good night, traveler. Good night, stardust. Good night, consciousness. Good night, universe looking back at itself. Sleep. Dream. Rest. The black hole waits in the darkness, mysterious and patient. The stars shine in the night, ancient and eternal. And you rest peacefully, safely, a brief flicker of awareness in the cosmic night, precious and beautiful and exactly as you should be. Good night.